Okay. Today
Maybe 5C1.
we want to do what's called probability distributions. So what a probability distribution is, it's kind of a table of all the possible outcomes and the probability associated with each outcome. Okay? So let's do an example. For instance, let's say I'm going to flip a coin, and I want a probability distribution for flipping a coin. Okay? So you have your outcomes for this and the probability for each outcome. Okay, so all of these probability tables look like x and p of x, which is the probability. In this particular example, if I flip a coin, what could happen if I flip a coin?
Heads or tails.
Heads or tails, right? And those are the only possible outcomes. So we have x can be h or t. And what is the probability associated with getting an h? 1/2. And 1/2 for tails. Okay? And that's it. So there's really two requirements. Okay? You have to have, well, I guess there's three requirements. You have to have every possible outcome, the probability associated with each. Okay? These have to be probabilities, and probabilities are locked between 0 and 1. And the other thing that has to happen is if I add up all of the probabilities, and you've listed everything, what must this add up to? 1. Exactly. Okay? Let's do another example. Let's roll a die. Can you show me a probability distribution for rolling a die? Okay? And this time, let's make the table this way. X and P of X. If I roll a single die, what are my possible outcomes?
1, 2, 3, 4, 5, and 6.
Yep, 1 through 6. And then again, very similar to the last example, in this one, the probability is the same for all of those, right? So what's the probability of getting a 1? 1, 6. On and on and on. And again, this is my probability distribution. Okay? All right. The first formula we have is finding what we call the mean or the expected value from our probability distribution. Okay? So it could be asked either way. They could say, hey, what's the mean or expected value from a probability distribution? Okay? And here's your formula. It's equal to the summation. So we've seen that before. What does that mean? I'm going to do what? Add stuff, right? So each x, so I'm going to put a little xi here because there's more than one x, right? So every x times the probability of each of those x's. Okay? This is my formula for the mean or the expected value from our probability distribution. Okay, let's do the last example we just did with rolling a single die, right? So I had one, 2, 3, 4, 5, and 6. All of these were 1/6. So I would get the summation. I'm going to add up the first x times that probability. So 1 times 1/6 plus the second 2 times 1/6 and on and on and on. Plus dot 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 up to 6 times 1/6. Okay? So go ahead and take a minute and calculate that, and that's going to give us our expected value from this probability distribution. See what you get. What did you guys get?
Also,
1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6.
yeah, 3.5.
3.5? Okay. Now let's talk about the meaning of that for a second. This is saying if I roll a single die, on average I expect to get a 3.5. Okay? Do I expect to get a 3.5 if I roll a single die? First of all, is it even possible to get a 3.5? No, it's not even possible. Okay? In this case, in this rolling a single die, all the probabilities are the same on each of these. Okay? So no matter what, you had the same probability. So really, when I roll a single die, the probability of getting any one of these is the same. Okay? So I don't really have this average or expected value. It's giving a 3.5 because it's kind of the average center value of this. But really, in the context of this problem, this 3.5 doesn't really mean anything. Okay? Does that make sense? So it's saying on average you should get a 3.5, but not really, because if I roll a single die, I have a 1/6 chance of getting either of those. All right. Let's take a look at some problems where we can attach a meaning and it makes sense. A lot of these problems are game-like, so they can be kind of fun in that sense. So let's do this first one. A box contains 10 $1 bills, 5 $2 bills, 3 $5 bills, 1 $10 bill, and 1 $100 bill. All right, so I have a box. And inside this box, we have 10 $1 bills. So 10 $1 bills. We have 5 $2 bills. We have 3 $5 bills. 1 $10 bill. And 1 $100 bill. Okay? And this game is called Charity Box. All right, here's how it works. You pay $20, and you grab 1 bill. Okay? And then the question will be, there'll be 2 questions. The first thing I'll ask you to do is find the expectation of the game. And the second question will be, is it fair? Okay? So find the expectation. So that is talking about this expected mean from a probability distribution. And then the question is it fair? If a game is completely fair, then the expectation should be, if we're talking money, 0. Okay? You should expect if you play this game to get 0, earn or lose 0. All right? Okay, let's build the probability distribution first. So I'm going to reach in to this box and I'm going to grab a bill. What's a probability that I grab a $1 bill?
Oh,
10 out of, how many bills do we have?
20.
20. So 10 out of 20. Does everybody see that? Which comes down to 1 out of 2. But just for the sake of your notes, I'm going to put 10 out of 20 so you can see where that came from. Okay?
yeah.
How many $2 bills are there?
5
5 out of 20. And we could also win $5. What are the chances of winning $5? 3 out of 20. What's the chance of winning $10? 1 out of 20. And $100. 1 out of 20. Okay, so here's my probability distribution. So what I want you guys to do right now is calculate the expectation or the mean of this. Same formula that we just utilized, okay? So you have the summation of each x times the probability of that x happening, all right? So each x times the probability of that x. So you're going to have $1 times 10 out of 20 plus $2 times 5 out of 20 plus on and on till you get to $100 times 1 out of 20. Okay, and that's going to calculate for you guys on average how much you expect to draw out of this box. If you play this game over and over and over, on average, how much do you expect to draw out of this box with one bill? Okay, so go ahead and calculate that. And when you finish that, tell me how much you get. Did you guys get $7.25? Okay, so let's talk about the meaning of that. If I just draw one bill over and over and over, on average, I expect to get $7.25. Okay? Now again, that's not a possibility, but on average, if you play this over and over and over, you're expected to draw $7.25. Okay. Now, I haven't factored in one thing though. How much does it cost to play this game? $20. Okay. So the expectation of this game is, on average, what we expect is $7.25 minus, of course, your cost. It cost you $20 to play it. And if I subtract 20 from that, what do I get?
Negative 12.75.
Right. So if you play this game over and over and over, you expect to lose $12.75. Okay? Is this game fair?
No.
No. If it was 0, it would be fair. Okay? Now, does that mean if you play this game once, you're going to lose $12.75? No, right? You could draw a bill. It could be a $100 bill. You might have made money. Or it could be a $1 bill. You might have lost 19. Okay? But over and over and over, on average, what do we expect? In the long run, you're expected to lose $12.75 playing this game. Okay? That's how it works. Let's try another problem. If a player rolls 2 dice and gets a sum of 2 or 12, she wins $20. If she gets a 7, she wins $5. All right. The cost to play is $3. So now we're shifting gears. We're going to roll 2 dice. So game number 2 here. Roll 2 dice. Okay? If you get a sum of 2 or 12, you win $20. If you get a 7, you win $5. And it costs $3 to play. Okay, just like the last problem. Find the expectation of the game, and is it fair? First, you need to start with building your probability distribution table, okay? So I'm going to get you started on that. You could get a 2 or a 12, right? And that wins $20. When I roll 2 dice, how many possibilities are there?
36.
36. What is a 2 or a 12 in those 36 possibilities?
1 out of 36.
Yeah, getting a 2 is a 1 and a 1. That only happens 1 out of the 36 times. Getting 6 and 6 is the only way to get 12. So that has a total possibility or chance of 2 out of 36, right? You might have to go back and look at your sample space on some of these problems. Rolling a 7 will win me $5. How many ways are there? Take a look at your sample space back on whatever page that is, and look at how many different ways you can get a 7.
Six.
6 ways? Okay. Does everybody see those 6 ways? And if you don't, you can just look on page,
184.
is it 184? Thank you, sir. 184? No, that's the parts. Oh, no, yeah, you're right, sorry. At the top, page 184, thank you. And find that there are 6 ways of possibilities, 6 possibilities of getting a sum of 7. Okay. 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. All right. And that's it. So what else could happen? I could win $0, I guess. What else needs to happen to finish a probability distribution table? I have 2 out of 36. I have 6 out of 36. What about all the other things that can happen? What's that going to be?
The remainder.
Right, the remainder, right? Because this has to add up to what? 1. Right? For a probability distribution table, it has to add up to 1.
28 out of
So 28 out of 36. Great. Okay, does everybody see that? So these all have to be probabilities. You have to list everything, and that probability has to add up to 1. Okay, from there you guys can take it. Find the expectation. So 20 times 2 out of 36 plus 5 times 6 out of 36 plus 0 times 28 out of 36. Luckily, 0 times anything is 0, so I don't really have to worry about that last piece.
So you just got to worry about the 2, the 20, and the 5?
Yeah, just because 0 times anything is 0. I mean, technically you have to worry about it in terms of finishing your table, but just multiplying is not going to do anything. All right, so 20 times 2 out of 36 plus 5 times 6 out of 36, we get 1.94 repeated. So this comes out to $1.94 approximately. What do I still need to add in? How much it costs to play the game, right? So take your 194, subtract cost. So 194 minus $3. On average, you expect to lose $1.06. Okay? If you play this game over and over and over and over, on average, you expect to lose $1.06. Okay, a lot better than the charity box anyway. Is it fair? No. Okay, comes out to 0, it would be fair. Questions on that example? Okay, so there's 2 things. We've done the mean, or the expected value. So you need to know that formula, but there's another formula, finding the variance. Okay, so how do you find the variance from a probability distribution? And here's what that formula looks like. Variance. It's the summation. This time you're going to square each of those xi's. So xi squared times the probability. Okay? So you sum each x squared times the probability of x, add all those up, and then you're going to subtract the mean. Okay? Subtract the mean from here, squared. And that's your variance one. Alright, so let's do one easy example. Let's make up one real fast. Let's say these are the only possibilities, and these are the probabilities associated. Let's do 1/2, 1/4. If I left that blank, would you guys be able to tell me what this one has to be?
Sure.
Sure, you would. What is it? 1/4. How do you know?
That's
Has to add up to 1, right? It's probability distribution. Okay? Alright, so last example, I want you to calculate the mean and the variance using this probability distribution. Okay? So let's do the mean. It's just x, the summation of x times b of x. So for this problem, it's going to be 0 times 1/2 plus 1 times 1/4 plus 3 times 1/4. Okay? That will give me the mean of this probability distribution. So go ahead and calculate that real fast.
Again, that 0, you don't have to worry about that 0, right?
Right, the 0 is really nice, right? What does this come out to?
1.
1.
Yeah.
Okay? That's a really nice example that I gave you so far. Alright, now find the variance. So how does the variance work?
Square your x.
Yeah, the x's are squared. So 0 squared times 1/2 plus 1 squared times 1/4 plus 3 squared times 1/4. Okay, and then almost always I have students do that part completely perfectly right, and they forget one thing. What do they forget? Minus the mean squared. Okay? So minus, we already did the mean, 1 squared. Okay? That's the variance formula. Take each x and square it times the probability of that x. Add those up, but don't forget to subtract the mean squared. Okay? And this comes out to,
1.5.
I don't know, I'll let you guys tell me.
1.5.
Let's see, well, this is easy, right? So that's 0, so we're going to get 1/4 plus 9/4 minus 1, which is 4/4. Right? So 10 minus 4, 6/4. What is 6 divided by 4?
1/2.
1.5. Did you guys get 1.5?
I did.
Did I do that right?
Right.
Make sure. Everybody get 1.5?
I did.
All right. Any questions on that? Okay, so this was the mean, or the expected value, and variance from a probability distribution.